Yeah, so today we are very happy to have Andrew Hardt speaking about Schubert calculus stability. So please go ahead.
Great. Yeah, thanks so much. Thanks to the organizers for the invitation. I'm really thrilled to virtually be here. So I'm going to talk about a couple of papers, mostly one of the two. Both are joint with David Wallach. Um, and so before, sort of as the first thing, I'm going to do an algorithm without explaining anything about why we're doing this algorithm. So we're going to choose two permutations. It can be any two permutations, but in this case, let's have U be 21543 in one line notation, and then V is 52413. So let's write this as 21543, and we're going to draw the dual rotodiagrams. And so the usual rotodiagrams, the death rays go down and to the right. These are sort of the Empire Strikes Back version where they go up and to the left. And the dual rotodiagram is going to have the boxes in the usual manner. So we have a box here, boxes there, and a box there. So that's the dual rotodiagram for U. Now for V, 5, 2, 4, 1, 3, we do the exact same thing. Okay, boxes aren't so straight, but I hope we get the picture. So here are the dual rotodiagram. So that's step one. Step two is we count the non-empty rows from bottom to top. Okay, so for the left one, that just means a 1 because the bottom row is non-empty, then a 2. Then we have an empty row, so we're stuck at 2. Then we have another non-empty row and another empty row, so those are the counts. And then on the right side, the bottom 4 rows are all non-empty, and only the top one is empty. Step 3, we add across each row. So add the entries in each row. We'll call row I the ith from the top, and add to that I minus 1. So I minus 1 is just, sorry, it should be 0, 1, 2, 3, and 4. And then the totals are, let's start from the bottom. 1 plus 1 plus 4 is 6. 2 plus 2 plus 3 is 7. 2 plus 3 plus 2 is also 7. Then 3 plus 4 plus 1 is 8. And then we get another 7. And then finally, we just circle the largest total. Okay. And so that's our algorithm. And so it turns out that the number that we've circled is exactly the smallest integer n, such that if we take the Schubert product, Schubert U times Schubert V, and we expand it in terms of Schubert W's, every W appearing on the right side with a non-zero coefficient lives in Sn. So Sn is the smallest symmetric group containing all of those permutations W. And so we're going to call this the forward stability number. Okay, before we move on, I want to check our work. So hopefully, can you now see my Sage terminal?
Yes.
Excellent. Okay, so let's set U and V to be the permutations from above. So 2, 1, 5, 4, 3. And V is 5, 2, 4, 1, 3. And let's just do this product, Schubert product of U and V. And notice we get a whole bunch of permutations, and you can see that they lie in different symmetric groups. Now, in some sense, they lie in every larger symmetric group because we can embed Sn into Sn plus 1 in the usual way by fixing the last entry. And so notice some of them live in S6, some of them live not in S6 but in S7, and then a few of them live in S8 and nothing smaller. And so the largest number moved, or the smallest symmetric group containing all of them, is indeed 8. It's exactly what our computation got, luckily. Okay, so I want to talk about another algorithm, but first let's do a little bit more experimentation here. So I want to choose two other permutations just to make it simpler. We could use these, but the computation is a little less obvious to see. So 2, 4, 1, 3, and 4, 2, 3, 1. And I'm going to again do the Schubert product of U and V. And here we have a sum of only two Schuberts, right? One lives in S5, the other lives in S6. But what I'm going to do this time is we're going to manipulate that Schubert product to get more terms. So if you push a permutation forwards, what that means, sometimes people call this, Lamley and Shimozono called this gamma. Often people just call it 1 times W. So what happens if I push 2, 4, 1, 3 forwards? What I'm saying is instead of acting on the first 4 integers, I want to now act on integers 2 through 5. So see, I've taken these 4 numbers, and basically what you do is you increment each one by 1, and 1 is now fixed here. So it's a permutation just acting on different integers. And we could push it forwards again, and now 1 and 2 are fixed, and the sort of non-trivial part of the permutation acts on the integers 3, 4, 5, 6 in the same way of the original. And so we can ask what's going to happen to the Schubert product if I push both permutations forward by 1. And so now I'm multiplying, again, I've pushed U forwards 1, I've pushed V forwards 1, and I get a longer list of permutations out, right? But the two permutations that appeared here also appear pushed forward with the same coefficient. So let's push this one, 5, 4, 2, 1, 3. And if I push that, then I get this permutation that does indeed appear in the Schubert expansion with the same coefficient. Okay, and so this is well known to happen this way. In general, pushing forwards these permutations does not change their coefficients. What does change is that we've acquired some new permutations, and notice the new ones we've acquired only, like none of them fix 1, because if they fixed 1, they would have appeared in this Schubert product. So we've got a whole bunch of new ones. Let's try pushing it forwards a second time. And we have almost the same list of permutations. Each one is pushed forward one more step. Notice that this one had coefficient 2. When I push it forward, I get this permutation. It still has the same coefficient. I've acquired now 2 new permutations, 1, 3, 8, 4, 2, 6, 7. Sorry, not that one. That one is not new. 2, 3, 6, 5, 4, 1, and 2, 3, 7, 4, 5, 1, 6. Let's try pushing forward again. And that took a little bit longer, but notice that we didn't acquire any new permutations here, right? All of them start with a 1, meaning all of them were old from the previous step. Let's keep going. Takes a little bit longer here, but we again acquired no new permutations. Every permutation that we have on the right-hand side of this product was seen at step 2 or earlier. Okay, so I'm going to go back to sharing, but just remember for that example that we had to push forward exactly twice to, at least in theory, get all of the permutations. Okay, I'm trying to share again. Okay, this is a problem. Sorry about the technical issues. Okay. Let's see if this works now. Gosh, apologies for this. I practiced about 10 times and it never happened like this once.
Yeah, Zoom is always our friend.
Yeah. Okay, I'm still going here. I think it'll just be another minute. I have to reset the Wi-Fi. Well, while we wait, we can try pushing forward a 5th time, and that'll take a few seconds to do the computation. Okay, and so we again get no new permutations. Here we go. Excellent. Okay, so we're back. And let's now sort of give rigorous definitions of what we've looked at so far. So
So
first definition.
we still
Oh,
see the Sate screen. Here we go. Yes,
okay.
great.
It's there. Okay, excellent, excellent. So, okay, so definition, let's let U and V be permutations of positive integers. So whenever I write S sub some set, I'm just talking about the permutations of all of the integers in that set that fix all but finitely many integers. And so the forward stability number is just the thing that we got from our first computation, which is just the minimum value of n such that for any non-zero Schubert structure constant, W lives in the symmetric group on n letters. And the second definition, the back stability number, is going to be the minimum k non-negative such that when the back stable Schubert structure constant is non-zero, W lives in the set of permutations where I start from 1 and go back by at most k. Okay, so it fixes everything less than 1 minus k. Okay, that's not the definition that we've gotten from our example, so let's say it a different way. It's the maximum value such that when I push forward like we did in those SAGE examples, that we get a new permutation. Okay, we get a new permutation on the kth push forward, and we never get any afterwards. So that's the definition of the back stability number. How many times do we have to push forwards? So Lascaux and Schutzenberger, all the way back in 1982, developed Schubert polynomials and generalizations thereof. And so the fact that those are polynomials that are stable across all symmetric groups, as long as they're large enough to include the permutation, means automatically that this forward stability number is going to be finite. Because all you need to do in any symmetric group, you just multiply the Schuberts, and then you expand, and then whatever that expansion is, there's a finite expansion. There's some largest symmetric group that you need to contain all of that. And then for the back stability number, Nan Lee in 2012 explored this concept in the context of products of Stanley symmetric functions. And she showed that this back stability number is always finite. And in fact, she gave a bound on the back stability number. It's always less than or equal to the sum of the lengths of the permutations. And at the same time, Lee conjectured a stronger bound. So if you notice, the Coxeter length of a typical element in Sn is on the order of n squared. And Lee's conjecture, I'm not going to write the specifics, but she conjectured a specific bound that's linear in n. She conjectured something else as well that we'll call the no gaps conjecture. And the no gaps conjecture is simply that when we do that pushing forwards, notice that we got new permutations, then we got new permutations, and then on the third step, we did not get any new permutations. And Lee's conjecture is as soon as you have a step where you don't get any new permutations, then you're done getting anything new. So the very first step that doesn't give you anything new, you're done. And so that's the back stability number. And so that if that conjecture is true, then it would show that indeed the back stability number for those two permutations is exactly 2. Okay, and then Asaf and Searles in 2016 worked on this problem, and they improved Lee's bound on the sum of the Coxeter lengths, although their formula is still in general quadratic in n, the size of the symmetric group. Okay, so before I talk about results, I'm going to give another algorithm that will compute. So before I talk about results specifically, I'm going to give an algorithm that will compute on the nose this back stability number Bs of U and V. So these two permutations are the two from the example before. And this time we're going to draw the rotodiagrams, not the dual rotodiagrams. So 2, 4, excuse me. 1, 3. Okay, and so now for V, 4, 2, 3, 1. Okay, and then I'll draw these boxes. Okay, so that's step one, to draw the rotodiagram. And now we again count the non-empty rows. Here, I'm going to move this down. Count the non-empty rows, but this time from top to bottom. Okay, so on the left, we have a non-empty row, empty rows, so we stay at 2, empty rows, so we stay at 2. And the one on the right, we have 1, 2, 3, and then another 3. And then third, we add the entries in row I and subtract the number I. And finally, like in the previous algorithm, we circle the largest total. So here's the column for -I, -1, -2, -3, -4. And now our totals are going to be in the top row, 1 + 1 - 1 gives a +1. 2 + 2 - 2 gives a 2. 2 + 3 - 3 gives another 2. 2 + 3 - 4 gives a 1. We circle the largest. Doesn't matter which 2 you circle. That is the back stability number. Okay. So that's the algorithm. Let's talk about this a little bit more formally. So let's let little theta sub I be 1. It's going to be 1 if and only if there's a non-zero ith row in the lemur code. And big theta sub I is exactly the same except for the dual lemur code. And then big lambda and little lambda are the sums of the non-empty rows, those counts going from either the top or the bottom, depending on which one we're using. And so our theorem is, number one, Lee's conjecture is true. So both her no gaps conjecture and the bound that she had for it, they're both true. And moreover, we can give these specific formulas that I've told you the algorithms for both the back stability number and the forward stability number. They equal these exact things. Excuse me. So I just want to remark that you might have noticed that these formulas are very similar, right? They're almost dual. We're doing one where it's the rotodiagram, the other is the dual rotodiagram. We're counting in different ways. We're adding or subtracting something like I. And these formulas are indeed closely related. In particular, the formulas themselves are actually dual. In the sense that if I have a Schubert structure constant, CUVW, and they all live in some SN, then if I just conjugate each of them by the longest element, it's well known that that fixes the Schubert structure constant. It's unchanged in that case. And so this formula is essentially what you get, these relationships between these formulas, if you do that to all of the permutations you conjugate by W0. However, the results themselves are not actually dual. The reason being that the back stability number uses back stable structure constants and the forward stability number uses ordinary structure constants. And so it's not exactly the same to say that these results are equivalent. In fact, there's a significant technical hurdle in going between these sets of coefficients. Okay, a second remark is I've been talking about ordinary cohomology, just ordinary Schubert polynomials. But if you take the same definitions of forward and back stability numbers for equivariant cohomology, ordinary K-theory, or equivariant K-theory, we get exactly the same formulas for those two numbers. And so one consequence of this is a new proof of a conjecture of Lamb, Lee, and Shimozono that was originally proved by Anderson by very different methods, which is that the back stable double Grothendieck polynomial expands as a finite sum of back stable, or sorry, I should say products of back stable. Oh yeah, sorry. No, this was right originally. the backstable double growth indique product expands finitely as a sum of backstable double growth indiques. So this was conjectured by Lamley and Shimozono and proved about a year or so ago by Anderson. Okay, and so here's another corollary, which is you can use the same ideas as the back stability number and the forward stability number to say exactly what the set of simple reflections appearing on the right-hand side of a Schubert product are. And these are in some sense equivalent in that if I know the forward stability number and the back stability number, then I know the simple reflections corresponding to those extremal elements. And then in between, in many cases, in all kind of non-trivial cases, just every simple reflection in between is going to be part of some expression, except in the case where they sort of factor in some trivial way. But the point is that the following algorithm tells you exactly what simple reflections appear in such a product. So for time reasons, I've done this already, and I'll just talk through it. So what we do is we choose two permutations. Here I've chosen some short ones. U is 3, 2, 1. V is 2, 3, 1. And we underline any entry that exists to the right of a larger number. And we put an overline on any entry to the left of a smaller number. So here we have underlines, underlines, overlines, underline, and two overlines. And then step 2, we draw an up arrow in row I if the ith entry of the permutation is underlined. Let's see if I can see these permutations. And a down arrow if the entry in row I is overlined. So there's a shift by 1 just because the simple reflection SI swaps I and I plus 1. So that's why there's a slight discrepancy here. But so here we have underlines in entries 2 and 3. So we then have up arrows in rows 1 and 2, and then overlines in entries 1 and 2. So we have down arrows in 1 and 2, and then similarly for V. And then you can move the dots through the diagram according to the following rules. So here they are again. I just put them next to each other. And whenever I have two up arrows in the same row, for instance, this row, I can move one of them up. And what I'm going to do is I'm going to push them up as much as I can. So I push one up to this row. Now I have two up arrows here, and then I push one of them up further and I get a dot up in row 0. Similarly for down arrows, I have two down arrows here. I push one of them there. Now in this row, I have 3 down arrows. So I'm going to push 2 of them down to this row and then 1 of them down to that row. And so finally, I end up with a dot in row 1 or 0, 1, 2, 3, and 4. And then the set of the dots that exist in the column W exactly equals the set of simple reflections that appears somewhere on the right side of the backstable Schubert product. If you want the ordinary Schubert product, that's just fine. You just cut off, you draw a line here between 0 and 1 and throw out anything above this line. Okay, I think this is a good time for the break.